when we look at the schedule, we are technically in week 8, I believe. 9. We're in week 9. So we're going to be doing a review of contrast this morning, and your test will open up. It's probably already open. I think I opened it at 7:30 or 8. So your test will be open up till Thursday, and then we'll do practical this week. But the good news is, once you're done with practical and lab this week, then we're not starting new stuff. That'll be next week when we start AEC. So you'll have some time to take your test or study some more and then take your test for this week, because you haven't learned anything new in Yolanda's lab either for us to need to use that time for peer review. So, so that's the plan for this week. Next week we start AEC, which I love. Hopefully y'all.
Excuse me. Have anybody took the test yet?
No, because it literally just opens.
Is it possible to make it too private?
No. It's easy. No. I don't like tests being open on Friday because of the college's OIT stuff that happens on Friday. A lot of times we don't have access to certain parts of Blackboard, and it seems like things tend to go wrong on Fridays, especially in the afternoon. So once that OIT stuff starts, so I've always just shut them. And plus you're going to have extra time from lab this week to take your test. So, yeah. All right. So what I want to do first is, hopefully you saw it. There's a PowerPoint that just sort of summarizes a lot of the stuff that we did 2 weeks ago, and then 2 weeks ago and then last week. And so hopefully this is going to pull all this information together, and then we'll have time for questions. We're going to I'm sure we'll have time to look at the study questions. And if there's something on there that you're not sure about, then we can also look at that. Everybody. All right, so let's look at some review of contrast. And then I'm also going to do a little demonstration that I hope will work and help us to understand attenuation, that term. But defining image contrast. So contrast is one of 2 photographic properties that comprise visibility of detail in an image, with the other one being receptor exposure. So we have what we call photographic properties, and then we have geometric properties. We haven't gotten to the geometric properties yet. That's coming towards the end of the semester. So when we start to talk about spatial resolution and size and shape distortion, those are geometric properties. Contrast and receptor exposure are photographic properties. And so some of this comes from actually when we were on film, and we would talk about it that way, but we can still use those terms appropriately even with digital imaging. So the difference between 2 adjacent brightness levels is what we are using to define contrast. Okay, the contrast, the difference between brightness levels that are adjacent to one another. So if we are talking about high contrast or increased contrast, then we're talking about a great difference between those brightness levels. We can also refer to that as having short scale or short grayscale. The image is going to appear more black and white. The black is blacker, the white is whiter. And so we'll see an example of that. Again, this was a lot easier to teach on film, because you actually, when you hung the image up there, that was your display contrast. Your subject contrast was your display contrast. You could see it. You could see the difference. Now with digital imaging, what is basically in control of the display contrast? The computer. the algorithms that were used to process it, whether or not you make adjustments to the contrast, post-processing of the image. So easier to sort of understand with film, but we still have to talk about it. So an image with high contrast would look something like this, where it is more black and white. The whites are whiter, the blacks are blacker. So there's greater difference between the brightness, adjacent brightness levels. We can also talk about low contrast or decreased contrast or less contrast in an image. And that's when there's small or very little difference between the brightness levels. We can also refer to that as long grayscale, or the image having many shades of gray. So remember, low contrast, long grayscale, lots of shades of gray. So the LOs, low contrast, long grayscale, lots of shades of gray. And then the opposite would hold true for higher contrast. So this image would represent a lower contrast image. There's not those really bright areas that we saw in this same image previously that had the higher contrast. So any questions up to that point? Pretty much review. Hopefully, if it wasn't, it's making more sense now to you. So that's really what we've been so far been talking about. Display contrast. Okay, how does it look on the image monitor? Subject contrast is that contrast that comes from the patient. Okay, so from the patient's body, their anatomical parts. And so we can talk about subject contrast as being the range of differences in the intensity of the beam after it has been attenuated by the subject. So a couple of words in there that we need to understand. Again, intensity meaning what? Quantity, number, right. So the difference in the quantity of the beam after it has been attenuated by the subject. So attenuation, you should have seen in your RadTech Bootcamp video whenever you did it. Attenuation means a loss of intensity due to either what? What are the two interactions? Scatter or absorption. So loss of intensity due to one of those two or both of those interactions. Another way to say it is the difference in radiation intensity between the various portions of the remnant beam after passing through the patient. So it's saying the same thing. Remnant beam meaning what?
Like leftover.
The leftover. What made it through the patient to actually get to the IR and interact there. We could also call that exit beam. All right, so the primary is coming from the tube directed at the patient, and then exit is what exits the patient, what's remnant, what's left over. So subject contrast depends on KVP. That's the controlling factor. That's the thing we can control, right? Can we control part thickness? No. Can we control average atomic number? No. Can we control part density? No. So the controlling factor of subject contrast is KVP. These other things do affect subject contrast, but those are patient related. That's not anything that we can change. The only one of those that we can possibly adjust a little bit is part thickness through what we call compression. So we used to have, I've not seen it, well, it's common in mammography. You guys are really young, so none of you have, anybody in here by chance had a mammo yet? Okay, well, get ready. So with mammography, they compress the breast tissue down like you're in a vice, okay? And so that changes the part thickness. We used to have these big compression bands that would hook from one side of the table to the other, and we would use those for a couple of things. Typically, it was to help keep contrast in the kidneys when we were doing IVUs. Okay, so we would put these compression bands across the patient and it would flatten the patient out somewhat, compress them down, make them a little bit thinner. But typically you're not going to see that. I haven't seen that done in a very long time. So KVP and subject contrast, we just said KVP is the controlling factor of subject contrast. We know that as KVP increases, the average energy of the beam increases, right? So as KVP goes up, the average energy of the beam is going to go up. The penetrating ability of the beam increases, so we're going to get more uniform penetration of the parts. Overall, as KVP goes up, we're going to get more transmission and less absorption overall, right? But related to one another, when we compare the amount of scatter to photoelectric, as KVP goes up, scatter increases compared to photoelectric, right? So overall, if you increase the KVP, there's a better chance that no interaction is going to happen. But compared the two side by side, meaning Compton and photoelectric, then as KVP goes up, you're going to have more percentage of Compton scatter than you will photoelectric. Is everybody with me? Okay. So this is the image that actually is in that little short video, and this was also in your PowerPoint from a couple of weeks ago, talking about KVP and subject contrast and how you can see the difference. So here the image on the left was, and the 6 is almost cut off. The image on the left was done at 68 KVP, and the image on the right was done at 106 KVP. So you can see which image has lower contrast, left or right? Right, the one on the right, because it's more gray. You see how, look especially at like the washer area, the washer that I've got on there, and the SI joints. See how those areas are much brighter in the one done on the left than on the right. And so the only thing that changed between those two images was the KVP, well, and the mass adjustment for that, because we're going to talk about that in a minute. How if we change KVP, we have to make a mass adjustment to go along with that so that receptor exposure is maintained or stays the same. So the only difference was that we adjusted the KVP up, and the display contrast, as you can see, displays the difference in the subject contrast with film. We lose that with digital imaging. So any questions about that? Okay, now's the time. All right, so let's look at some of those other 3 things that affect subject contrast. So we talked about part thickness. So when the difference between adjacent thicknesses of various body parts is great, then the subject contrast increases. When there's little difference between adjacent part thickness, then the subject contrast decreases. And just think about it, that just makes sense. If there's not a lot of difference in the part thickness, doesn't it make sense that it would all look about the same? Right? So the contrast is going to vary little when we have little difference between the part thicknesses. Okay, when part thickness or talk about part thickness and field size and scatter. So when there's an increase in the overall thickness of a body part or an increase in field size, scatter increases and image contrast decreases if that scatter reaches the IR. So think back to the activity that we did in lab, and we said if there's more matter, there's going to be more what? Scatter. Okay, so we can get more matter by having a thicker patient, by having a larger field size, and by having a denser patient, okay, or part. So when there's an increase in any of those, then that's going to mean that's more matter to deal with. So it's going to be more scatter, and it's going to lower contrast always if that scatter reaches the IR. So we saw what scatter does by taping that foot onto the detector and seeing how that image was created solely from the scatter that came off of the abdomen that was there. The average atomic number. So when we talk about the difference in average atomic number increasing, then subject contrast increases. And when the difference in average atomic number decreases, then the subject contrast decreases. So what this is talking about is if you have two parts and one of them has a much higher atomic number than the other, then that's going to give you higher contrast. For example, bone and air. All right, so like the lungs, you have the bone and then you have the air. So that's going to be high contrast because there's a big difference in the atomic number of those structures. And then the tissue density. When the difference between adjacent tissue densities is great, subject contrast is increased. Again, also think about bone and lung tissues. There's the bone is much denser. The atoms are much more compact in bone than they are in the lung. And when the difference between adjacent tissue densities is little, subject contrast is decreased. So think about soft tissue that surrounds the kidneys and then the kidneys themselves. You're not going to see a lot of difference there on the image between those two structures. So the good thing about this is that all three of those things, when there's a greater difference, when there's more difference in that, then there's going to be an increase in contrast. So all of them have the same relationship. Was that a sneeze? Oh, okay. I was going to say bless you. So that makes it a little bit easier to remember. So when we are talking about selecting our KVP, appropriate KVP is going to be optimum for the part, which means it's going to penetrate through the thickest part and produce an acceptable amount of scatter radiation. Remember that changing the KVP affects both the quality and quantity of the beam, and that's where we're going next. But think back to lab again when we talk about optimum KVP. Okay, so that one activity where our KVP was way too low through the skull, that one area of the skull we could never see well, right? When the KVP was too low. And then also think to that activity where we ran the KVP up and we used 106 KVP. Do you remember how noisy that image got? So both of those are extremes. If it's too low, it's not good. If it's too high, it's also not good. So optimum just means you're going to get through the thickest part and you're going to produce an acceptable amount of scatter. So there's a balance there. Generally, we are given KVP ranges for parts, and then we adjust the mass to compensate for differences in thickness of the part. So when we increase the KVP 15%, if that's all we do, so let's say we just increase the KVP 15% and we change nothing else, then what would that do to receptor exposure? First of all, would it increase it or decrease it? It's going to increase it, right? By a factor of what? Somebody said it, 2. So if we just increase KVP 15% and we don't make a change to the mass to compensate, then we have doubled receptor exposure. Is everybody with me? It only takes 15% change in KVP to do that. What percent of mass did it take to double receptor exposure?
200.
Well, 100%, right? It took 100% more mass or a doubling of mass to double receptor exposure. So that's why we said KVP actually has a greater effect on quantity of photons than mass did, right? But we don't like to use KVP to control receptor exposure because it changes subject contrast. It changes other things about the beam that we don't necessarily want to change. So increasing KVP decreases subject contrast. That's an inverse relationship. So if KVP goes up, subject contrast is going to go down. Increasing KVP 15% would require a decrease of 50% or having of the mass to maintain receptor exposure because there are more photons created. Remember, this is the part that you got to get all of this to get all the points on the practical. Okay, so when we increase the KVP 15%, there's more photons that are actually created in the X-ray tube at the anode, and those photons have a higher average energy. Okay, so that is the reason that you have to make adjustments to your mass if your goal is to maintain receptor exposure, because when you increase your KVP, you got more being created and they have higher energy. So there's a better chance that they're actually going to make it through the patient and actually interact with the IR. Remember, increasing the KVP decreases the chance of any interaction occurring because there's a greater chance the photon's just going to be transmitted, right? But again, relative to each other, there's a greater chance of Compton scatter versus photoelectric absorption with an increase in KVP. Because photoelectric absorption happens when the energy is what? Lower, right? It doesn't have the energy to make it through the part. So think of it that way if you start to get confused. Lord, I might have to use one of my demonstration paper towels to wipe. Sorry. Nose is starting to run all just out of the blue here. I don't have any hand sanitizer here. Okay. Sorry about that, y'all. All right. Moving on. Is it making sense so far? Every this thing just sort of seem review, I hope.
Can you repeat the doubling part?
Yes.
What doubles?
Okay, so when we increase KVP 15%, the question is, okay, what effect does that have on receptor exposure? Well, when we increase KVP 15%, that actually doubles receptor exposure. It has the same effect that doubling the mass has on receptor exposure. So when we double mass, or we break mass down into MA in time, or we double MA, that also doubles receptor exposure. When we double time, that also doubles receptor exposure. So it has the same effect. So it only takes a 15% change in KVP to do that, whereas it takes a 100% change in mass or MA or time if you split it out. Does that make sense?
Yes, ma'am.
Yep. Yeah, good question. So the opposite also holds true. If we decrease the KVP 15%, then that's going to increase subject contrast because we're going to get more photoelectric absorption as the KVP is going down. Okay, so you're going to get a lot more absorption, which creates the really what areas on the image, bright or dark. If the photon is absorbed, does it show up as bright or dark on the image?
White.
Yeah, white, bright, brighter. Okay, the really dark areas are the areas that have gotten a lot of receptor exposure. So that means the photons made it through to interact with the IR. So in decreasing KVP increases subject contrast. It requires an increase of 100% or doubling to the mass to maintain receptor exposure, because when we decrease our KVP, now there's fewer photons being created in the X-ray tube, and they have lower energy. So there's going to be a less likely chance that they can make it through the patient's body and interact and contribute to receptor exposure. When we decrease KVP, it increases the chance of any interaction occurring because there's less chance that the photon's going to be transmitted. There's a greater chance that it will be absorbed with the decrease in KVP. Okay, it's not going to have as much energy. It's not going to have as much ability to make it through the patient as the higher energy photons do. And this was the example that I used with the car. If you have the same size car traveling at 50 miles per hour as opposed to 80 miles per hour, which would have greater impact if it hit your car. So the one traveling at higher speed is going to create what? More impact. So that's the same thing if you think about in sort of the same thing you think about in the X-ray tube. When we adjust KVP, it's adjusting the speed of the electrons going from the cathode to the anode, right? They travel at about half the speed of light, but the KVP does affect that. So the higher the speed of the electron going from the cathode to the anode is going to create more impact at the anode, which is going to mean more photons are produced at the anode when they are traveling at a higher speed. So think about the car. I'd much rather, and having gone to Charleston this weekend with my husband driving, I would much rather get hit at 50 miles an hour than 80. Nerves were shot by the time we got home. He thinks he is the best driver in the whole wide world. Nobody's supposed to be in front of him either. So anyway, we got some very nasty looks. Anyway, I don't know why I got off on that. Okay, so rule of 10. Between the KVP range of 60 to 90, then changes of 10 KVP can be used to change the KVP 15%. So what that's saying is between 60 to 90 KVP, if you're trying to change the KVP 15%, you can just change it 10 KVP, and that's close enough. That makes the math easy in the clinical situation. So if you're in clinic and you're using 70 KVP at a particular mass, and you want to increase your KVP, you want to change your subject contrast, or you just think it's maybe not penetrating well enough, then you could just go to 80 and do what to your mass?
Half it.
If I increase my KVP, what have I got to do to my mass? Half it. Somebody said it. Yeah. So increased KVP is accompanied by a decrease in mass if the goal is to maintain receptor exposure. Trying to keep it the same. Oh, that was the end of that. Okay, so what questions do you have related to that? Do we need to talk a little bit more about increasing KVP and decreasing mass, or opposite? So just remember, especially for those of you who have the practical today, because that'll be group 1. If you are increasing the KVP 15%, then you're going to do what to the mass? Cut it in half. So that's the math. You got to know how to figure out, okay, what is 15%, and how do we do that? Multiply the KVP by what? 0.15, right? Just finding a percentage. So you would multiply by 0.15, and then if you're increasing KVP, you would add that to the KVP that you're given, and you cut your mass in half. And the opposite would hold true. If your case is to decrease KVP 50%, you're still multiplying it by 0.15, subtract that number, and then do what to the mass? Double it. If your goal is to maintain receptor exposure, which that's what our goal is on the practical. We're trying to keep receptor exposure the same. Okay. All right. So let's look at the questions. Let's see. So this is the review PowerPoint we just went over is right here in this week's stuff. And this video right here is pretty short. Has anybody watched it? This one is a guy that I used to have. Let me see if it'll still. Yeah, let's watch this. You hear it? Is that too loud? So the difference in what we're doing in the lab and this is he's saying from the beginning, when he shot the x-ray, it was underexposed. So he needed to use more. All right. So he had two choices. He could either double the mass, right? The 40, or he could leave the mass the same and increase the KVP. So do you see how increasing the KVP and leaving the mass the same was a good decision in that case? Because it's saving the patient what? Dose, exposure, right? We've already exposed them once, is what he was saying. We've already exposed them once and it wasn't enough. Didn't use enough. So what he did was he said, okay, I can double that receptor exposure by increasing my KVP and leaving my mass alone, and that will save the patient some dose. If he had left the KVP at 70, then he would have had to double the mass to 40, which would mean even more patient exposure. Does that make sense? Okay. I like that. That makes sense?
Okay, I might be overthinking it.
Oh boy, here we go.
I don't
ahead.
think you are, because I think I have a question too. But
Okay, let's see if we have the same question. So I get that more are coming through, but once they hit the image receptor, the table, whatever the patient's on, isn't there gonna be scatter, and then that scatter is now gonna be absorbed by the patient, or do we not worry about that right now?
No.
We're not worried about that.
Your
Okay.
image receptor is generally not gonna create scatter that's gonna go back to the patient.
Okay. Okay, so because they're moving faster and can go through it.
Mm.
Ooh,
Are
not
they
faster. No,
moving
no, no.
faster?
They're moving, no, they're more.
So let me just say this real quick.
Okay,
So what changes speed is in the tube. of the
Okay.
electrons, not the speed of the photons. What did he say? The photons always, always, always travel at what speed?
Light.
The speed of light. So it's not changing the speed, it's changing the wavelength of the photon. It's changing the energy of the photon, not the speed. So when we talk about KBP changing the speed, we're talking about of the electrons in the tube. So two totally different things.
That might be one misunderstanding.
Okay.
So then my other one is the patient dose is being decreased because it's like the photons are going through it and not being absorbed.
Right.
Okay,
That's exactly right.
but we're not concerned about any scatter.
No,
back. Okay.
not from, no. The patient's body is the primary producer of scatter. Okay. So once the photons make it through to the IR, that's pretty much where they stop. That makes sense? It's sort of like what captures them is the IR. And that's the goal, is to have the photons make it to the IR so that you do have differing contrast so that you can see the anatomic structures. Like, in other words, if all the photons made it all the way through, would we see anything? Everything would look exactly the same, right? If all of the photons were absorbed, would we see anything? No, it would all be bright. So it takes both to create the image. Does that make sense? But yeah, your question is a good one, and we'll come back to that speed thing also when we talk about AEC. Students tend to want to think the photon speed changes with AEC as well, and it does. The photons always travel at the same speed, which is the speed of light. Does that help?
Maybe.
Ponder it some more, and then let me know if it doesn't. Was that your question too, Noelle? Or you had a different question?
Okay.
I may be just super tired and missed it, but at the beginning of this, he started with 70/20, did he not?
Mhm.
So he went up to 80, but then didn't half our map.
Because remember, I said he's telling you receptor exposure was too low. He didn't use enough to begin with.
Okay.
That's the difference. So he wasn't trying to maintain receptor exposure. His issue was he did it and it wasn't enough. So the image receptor was underexposed. So maybe it had a little noise showing up.
Okay, so
That help?
if you start with it too low, then you just.
Right. If you start with it not being exposed enough, then to double it to help that situation, then you would you could increase the KBP and leave the mass alone, which is what he was talking about at the beginning.
Okay.
What we're going to do for practical is the technique that I give you to begin with, hopefully, is going to be really close to target. So it's going to be close to target. We're just going to change it just for the heck of it and see if we can maintain that same receptor exposure.
But not in every case would you have to do them together all the
Right.
time.
It's a very specific to what you're doing.
Gotcha.
Good question, because I'm sure other people had that question. All right, that's good conversation. Okay, so let's go to the study guide and look over. We'll just pull the key up so that the answers are there. And then if you have a question about something, you can ask. So setting the KBP in the tube, how does it affect the photons produced? Well, we just said it determines the speed of the electrons that across the tube from the cathode to the anode, and then it affects the energy of the photons that are produced. Okay, so that's how changing the KBP affects the photons that are produced. Does KBP affect receptor exposure? Why or why not? Yes, it certainly does. It affects the number of photons produced and how many get through to the IR. What's the effect of a 15% increase on receptor exposure? So if we just increased KBP 15% and we made no other changes, what would that do to receptor exposure? Don't anybody else answer. I'm looking at Noel.
Sorry, I'm
So
sorry.
if we
You
just, let's say we just increased KVP 15%, that's
Uh-huh.
all we do,
Uh-huh.
like what the guy did
Yeah.
in the video. What would that do to receptor exposure? First of all, would it increase it or decrease
Well, if we didn't touch the other one.
it? And we increase KVP 15%, what would that do to receptor exposure?
It would, it's not gonna. I don't wanna
Somebody
answer
help
this
her out.
because I'm still a little confused, because I know that when one increases, the other one decreases, but you're saying that we're only, like, he just only did the one and kept the other one at the same.
That's if you want so. If you want to keep receptor exposure the same. All right, we want to maintain.
Yeah, so if we increase it, then we need a half the amount.
That's right.
Yeah.
But if we're purposely, like we did in lab, I keep getting shocked. Do y'all hear that? We purposely increased our KVP and we had the dosimeter on the table. I don't know if you remember that. So we had the dosimeter on the table and we started at 81 KVP, I think. And we increased it 15%. So we went to 93. What happened to that MR reading as we did that? And we did nothing to the mass. We just increased the KVP 15%. Do you remember what happened? Not specifically, but like not numbers, but what in general happened to that MR reading as we kept increasing KVP?
I mean,
Did it go up or down? Anybody? Up. We are increasing KVP and doing nothing to the mass. So if we're increasing KVP, that means there's going to be more photons produced coming out of the tube, and they're going to have higher energy, so there's a better chance they're going to make it through the patient to the IR. So what is that going to do to receptor exposure?
increase it like.
Yes. Because we got more of them, and more of them are going to get through. That's if we just increase KVP 15%. That has the same effect as if we had doubled receptor exposure. It only takes 15% change in KVP to either double or half receptor exposure. Is everybody following? You following?
A little, yeah.
Yeah.
Oh,
Okay.
yeah.
All right. So if I say we are just increasing KVP and we're not changing anything else, just what effect would that have on receptor exposure? It would increase it.
Yeah.
Yeah. If our goal is not to increase receptor exposure, we like the receptor exposure that we have. We want to keep it the same. Then if I increase KVP, what do I have to do to mass? That's
Okay,
right.
I got
Make sense? Okay, maybe that video I shouldn't show. I certainly didn't show it to confuse y'all. I thought it might help, but
I think I was just thinking that no matter what, when you always use that rule, one always has to do the opposite of the other. I didn't know.
yeah, if your goal
do
is
just
to
15.
keep receptor exposure exactly the same, then that's what you do.
Gotcha.
I'm back at speed. I'm sorry. So what travels at half the speed of light
The electrons,
in the tube?
yes. The
Okay.
photons
Are
always
I'm sorry.
travel at the
Okay.
speed of light.
I know that's not what we're talking
No,
about, but
it's
that's
okay.
where
It's okay.
I got stuck.
I got it. So it's the electrons, like when the
Yeah.
filament heats up and the little electrons are boiled off, they're waiting to go across. Then depending on what KVP you set is going to determine how close to half the speed of light are they traveling. It's going to vary a little bit. It's going to be close to half the speed of light, but that KVP is going to determine whether they're a little faster or not. Okay. Good questions. What does increasing the KVP have on subject contrast? We know as the KVP goes up, what happens to subject contrast? It goes down. Because as KVP goes up, the part is becoming more uniformly penetrated. So all those brightness levels are coming closer and closer and closer together. They're looking more similar. And if there's very little difference between those brightness levels, then we say that contrast decrease or is lower, right? Okay, so number 4 is what we're gonna do on the practical. Question number 4. If we change KVP and our goal is to maintain receptor exposure, then if we change KVP, we have to change mass to compensate. Number 5, what's the effect of scatter on a radiograph and why? Scatter always decreases contrast because it puts a fog across the entire image. So that's why we do everything we can to try to minimize the amount of scatter reaching the IR by either using beam restriction or grids, which we haven't gotten to. We'll do that next semester. What is subject contrast? That's the difference in attenuation of tissues of the remnant beam. So subject contrast is that the difference in how the tissues absorb the radiation. All right, differently, differential absorption. I don't know if I have that question on here or not. I can't remember. What affects subject contrast? Well, we know KVP is the controlling factor of subject contrast. What factors affect the difference in absorption of radiation? And I think I have this question on here sort of twice.
Oh, are those different questions? Because when you said what affects subject contrast,
Well,
we're looking.
several things do. KVP, tissue density, tissue thickness. I should have asked the question, what controls subject contrast? Would
Okay.
probably be a better way to ask that, because that same question is in here in just a second. How would you, let's see, what factors affect the difference in absorption of radiation, the tissue thickness, the density, tissue density, atomic number? So those questions could be combined. Okay, because all 4 of those things affect the difference in absorption of the tissue, because it depends on the KVP that's set. It depends on the thickness of the tissue, the atomic number of the tissue, and the tissue density, how closely compact the atoms are to one another.
But if you were to ask, I know you can't tell us, but if you were to ask a question like this in the test, and you were looking for just KVP, you would put.
I would have to say controlling, yeah. And so question 11, so I need to sort of combine these questions. Question 9, we'll skip, I skipped over, sorry. 9, how else could you describe low contrast? You could say long scale, long gray scale, or many shades of gray. How can scatter be reduced? By collimating the beam and using the grid. How is subject contrast control? KVP.
I thought the KVP also affected the difference. Because it changed the interactions of proton and ion.
It does.
So for A, would you also put KVP in there as well?
Yes, that's what I was saying. I really need to
Okay.
combine questions. That's okay. I really need to combine questions 7 and 8 into one question.
Understood.
What is another name for low contrast, long scale, or long gray scale? Did I just say that? When will low subject contrast occur? That's with use of higher KVPs. What is another name for high contrast, short scale? When will high subject contrast occur with use of lower KVPs? You could also talk about tissue density, thickness, atomic number in that question. I don't have those answers there, but that also would affect whether it's high or low contrast. The influencing factors of contrast, things like using the grid, using beam restriction, do affect or influence whether or not we see the reduction of contrast due to scatter. So we get into those 2 things at the beginning of next semester. What is question 17, what is the effect on subject contrast of increasing the mass? Why does it not change? When you increase or decrease the mass, why does that not change subject contrast?
Because subject contrast is not affected by mass.
Yeah, but that will get you half of the points, because it's not changing what? Quality. Did you say it will? Quality. Changing yes, energy.
Okay.
So mass is not changing the quality of the beam. It's not changing anything about the penetrating ability of the beam or the energy of the beam. So there is no change to subject contrast. Where are we? 18. What is the effect on contrast or subject contrast if SID is increased or decreased? There is no change, because again, changing the distance, did it change one thing about the quality of the beam? What does changing the SID affect? The what? Quantity, the intensity, right? So changing the SID does affect intensity. It affects the number of photons that are gonna be available to interact at the IR, right? As we change the SID, but it's not changing anything about the quality of the beam. So if you're asked if mass changes subject contrast, the answer is no. If you're asked, does SID affect subject contrast? The answer is no, it does not. How can subject contrast be increased in areas such as the kidneys? Well, we could inject contrast media, right? You're not really going to see the collecting system sitting inside the kidney, the ureters, all the way down to the bladder. Now, sometimes if the patient's bladder is really full, you can make out an outline of it, but are you going to be able to see anything much? No, because the subject contrast of the abdomen is inherently high or low? Low. So the only way we're really going to see like the collecting system in the ureters is to put some contrast in there, inject contrast. The two positive contrast agents are barium and iodinated contrast. The negative contrast agent would be air. So you see things like air done on double contrast GIs or double contrast enemas, or even like double contrast joints. So orthograms, you may see that air injected sometimes. What three things could happen to the beam as it passes through matter? It can be photoelectrically absorbed, it can be caught and scattered, or it can be transmitted with no interaction. Which two of the above, meaning in question 22, are responsible or make up high radiographic contrast? It would be those photons that are either absorbed or transmitted. Structures that are right next to each other is going to give you the highest contrast, right? It's either black or white. If there was no scatter, then it would be completely black and white. But scatter is always going to, change our contrast there, lower it a little bit. So in question 24, which image has higher contrast? The image on the left. The image on the right is supposed to like show you a little bit of a gray overlay there. How else could you describe high contrast? Be short grayscale, more black and white. What change in technique would lengthen the scale of contrast but maintain receptor exposure? So if we are trying to lengthen the scale of contrast or make it longer, which way is our KVP going to go? Up. She's going like this. Up. Right? So if the goal is to lengthen the scale of contrast but maintain receptor exposure, then if we increase KVP 15%, what do we got to do to mass? Cut it in half. That's right. And the opposite would hold true if we were going to shorten the scale of contrast, and that means KVP is going to go down. So if we want to maintain receptor exposure, what does mass have to do? Go up. Yes. Okay. So we have just a couple more minutes. I want to try to do this experiment. I tested it out in my office and it worked pretty good. I mean, it's another visual that maybe will help. So let me pull this over here and see if I can do this. Let me, I'm going to go ahead and stop the recording so it's not so long.